Okay, let's go ahead and get started. I'm Charlie Smith, Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. Foundation of the G-PST is a group of 6 system operators from around the world who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. ESIG is the lead on Pillar 1, and more information on the G-PST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to our monthly joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, we're going to be using the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG13 as the event code. The instructions are also at the bottom of this screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar is on the topic of Denmark's future energy islands, a large-scale 100% inverter-based offshore power system. This is a change from the previously announced topic of preparing a system operator environment for a 100% inverter-based power system, which we'll do sometime next year. But based on the number of registrations for this one, it looks like it's going to be another bestseller. The increased interest around the world in application of power electronics to T&D system operation and control, as well as applications for wind, solar, and battery plants and hydrogen production is intense. Today's webinar will feature Christian Frank Flytkjær, Senior Manager for Grid Analysis at Energinet, located at the European office in Fredericia, Denmark, where he's responsible for Energinet's stability and power quality assessment activities. Christian is the technical representative of Energinet to the G-PST Research Agenda Group. Energinet is one of the 6 founding system operators of the G-PST and a long-standing member of ESIG. Christian has been active in the work of the G-PST and in setting the research agenda through the Research Agenda Group. I've been on many calls with Christian, wrapping up at midnight his time. I can tell you he's one very dedicated fellow, and I feel very fortunate to have him here with us today. The webinar today will focus on Denmark's future energy islands viewed through the lens of a large-scale 100% inverter-based offshore power system, enabling very high penetration of wind resources in Denmark, which is already a world leader in terms of annual wind energy penetration. These offshore energy island power systems are being designed starting with a blank sheet of paper. This presentation will cover the power system design considerations and technologies which enable the energy hubs. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG13 to ask your questions. And without any further ado, let's go ahead and get started. Christian, I'll now turn it over to you.
Thank you very much, Charlie. Thank you for the warm introduction and for the work on G-PST and ESIG. It has been a pleasure so far, and I'm looking forward to the continued cooperation. Thanks a lot for joining this webinar. I will be presenting our initial thoughts on the planning and design of Denmark's future energy islands. And Ryan, could you change the slide, please? I will give a bit of background. Why are we building the islands? And then we're going to discuss the electrical system design of the energy hubs. We're going to have a look at the technical challenges, and then last in the presentation, a bit on analytical tools and models. Ryan, please. A bit of background on the Danish transition. We are about halfway through, a bit more on our green transition. We have to finish it in around 9 years on the electrical system, where we have to reduce CO2 emissions by 70% compared to 90. So we are in a hurry, and these energy islands are a mean for us to reach our goal in time. The 50 target is climate neutrality in Denmark. Brian, please. We have an equal ambition at continental Europe level. There's also an ambition for European level to be climate neutral in 2050. And one of the means of accomplishing this will be the North Sea, where we have a large potential wind we can harness. So there's a strategy to harvest more than 300 gigawatt offshore wind by 2050. One of the Green Deal, let's say, key documents is the strategy to harness the potential of offshore renewable energy. And one of the key aspects in this strategy is that we cannot continue doing what we have done today, where we build point-to-point HVDC interconnectors and then land in wind power either using AC or DC systems. We need a more hybrid system approach, where we can do what could be traditional AC grid planning offshore, and hence constructing, let's say, a European HVDC grid. Ryan, please. This could be a version of how this could look like. We are building the hubs in Denmark, but there are also other ideas. Our colleagues in UK just announced that they are also looking into an energy hub, and our friends in Germany and Belgium are doing the same. And then the idea is that we can interconnect these hubs and then use assets for transmitting power, for harnessing energy much more efficient than if we use the traditional approach. Ryan, please. So a bit of background on the islands we are constructing in Denmark. We are constructing two. The one in the North Sea is at first stage 3 gigawatt, and it has to be in operation in 2033. It has to be expandable to at least 10 gigawatts. The other island is at 10 gigawatt or 2 gigawatt offshore hub, and it has to be in operation in 2030. Contrary to the island in the North Sea, here we actually have an island already, the island of Bornholm, as you see on your right. And here the idea is that we will start and we will finish this island before, and then hopefully we can take some key learnings with us when we go offshore in the North Sea, where we have to construct the island as an artificial island. It's of course much easier to access transmission assets when they are located physically on an island. The idea is to interconnect both hubs with neighboring countries using interconnectors. There's discussions with a number of countries right now, and the idea is that this will be the first of the European energy hubs. Ryan? There is discussion on power to X. The production we have in Europe, we need to be able to store it, and power to gas facilities would be a means. We have to also to convert the whole energy system, meaning transportation and the other more heavy industry types of energies. And this will require that we are able to produce hydrogen, and there's discussion on whether this is most efficiently done on the island or we should do it onshore. the transmission of hydrogen through pipes is much more efficient than we can do with HVDC. But of course, the square meter price on such an energy island is not low. So it will be an economic decision of whether the power to gas plants will be onshore or offshore. Brian, please. This is an illustration of how such an artificial energy island could look like. It's a 50% public owned island, and then the rest will be privately owned, and it's up to the market to design the island. So this is an idea of how such an island could look like, just to show you an illustration. Ryan, please. Yes. So the first main topic is on the electrical design of the energy hubs. The task we have been given at Energinet is to plan, design, and operate the offshore hubs. This means the offshore power system we built from the beginning, the landing facilities, meaning the HVDCs, and the interconnectors to neighboring countries. This is, for me, a particularly interesting task because what we are doing is basically to design a power system from the beginning. Everything needs to be considered, and you have an infinite amount of degrees of freedom, and you do not have that luxury onshore. So of course sorry. I have a cold, so I need to mute sometimes to give a cough. Could you go one slide back, please? So what we're doing is basically designing a power system from the beginning, meaning that it will be an energy hub with only inverters and converters connected. And the learning experience here we can take onshore and hopefully facilitate a more efficient and a more reliable transition of the Danish system. We have added a task in this regard, meaning that every electron on the island should be measured, it should be quantified and qualified, and we should do what we can to share the data so it can be used not only by us folks in Denmark, but for the whole world. I think there will be many key learnings from constructing these hubs we can take with us onshore, both on tools and models and on control facilities, and so on and so on. Please, Ryan. So this is the project stages we are going through, and you can see the progress down left. The first we have to do is to identify needs and alternative solutions. There will be an economic and environmental impact comparison of the different solutions, and then there will be preliminary specification of the selected schemes. Next, in the specification phase, existing system properties will be identified and performance requirement for the schemes will be set. There will be preliminary design studies carried out. Then in the implementation phase, detailed equipment requirements will be set, and this is in cooperation with vendors where contracts have been awarded. Control and protection settings will be devised, and simulation of critical events will be carried out. Then after the design is over, we go to commissioning and to operation and maintenance. And here comes the major difference from other projects we have been carried out so far, that we have to expand the energy islands over time, meaning that basically after a few years of operation, we will start out all over, adding more wind, maybe power to gas, and maybe new interconnectors. The main difference compared to the projects we have worked on so far is that there's very little experience for each phase to build on. We are doing this for the first time, and this is not typically what we do when we have, for instance, to construct an HVDC link. Then we will have a long series of projects where we can rely on experience. So a lot of new things needs to be investigated, and many of these things that has to be decided basically require knowledge from later stages. So I will get back to this a bit later. Please, Ryan. One of the major decisions we have to take here in the beginning is the choice of topology. Either we can choose to connect the hub on the AC side as shown on the left, or we can connect it on the DC side as shown on the right. And I'll go through a few of the characteristics in the next slide. So please, Ryan. The AC hub, as we call it, is constructed using point-to-point HVDC solutions. And if we construct a bipolar HVDC system, then loss of largest unit will be equal to the rating of one of the pole. The complex system controllers I will get back to, and the potential connection of power to gas here is quite easy on the 400 kV bus bar. This is the system that reminds us most of the system we have onshore, where the next is significantly different. But please, Ryan, slide. One thing we have to do is to connect the hubs together, and if we have to connect two hubs that are constructed as I just showed, it will be using a point-to-point HVDC. So a full HVDC station at both hubs needs to be constructed to connect the slides or to connect the hubs. So this is of course not a cheap exercise, but it comes with the benefit that you have full control over the connection between the hubs, which will be clear when we look at the DC hubs, why it could be a benefit. So please, Ryan. The DC hub will be more complex, at least from a technology point of view. We will use the MultiTerminal technology, which is not very mature. There are a few systems in operation around the world, but nothing at this scale. The loss of largest unit will be the same as before, and also as before, complex DC control and protection schemes are required. The connection of load in such a system will be different. We have the AC bus bars at the AC side of the HVDCs offshore, and here we can connect power to gas, but this will be different compared to a single bus bar where there's direct connection to all the HVDCs. Major complication of such a scheme here is that for a cost-efficient expansion, a multi-vendor framework is required. Please, Ryan. So we talk a lot about multi-vendor interoperability in Europe at the moment. It's almost just as hot as the topic of grid forming. So, and this is because if we have to expand these hubs over time, we cannot lock ourselves into one vendor. It's quite clear if we look at the configurations that connecting these DC systems, if they are from multiple vendors, will require significant exchange of signals, and both a technical and a regulatory framework needs to be developed. Who's responsible in the case of events, and how operational schemes handled in terms of risk sharing and so on and so on. So interoperability is much more than a technical issue. It's highly regulatory and legal issue, and the whole aspect of sharing data and models will be a significant hurdle we need to solve to enable this technology. Ryan, please. The benefit becomes quite clear when we look at this scheme, this figure, and also if we think back on the possible version of the future where we need to connect these hubs. Compared to the AC hubs, here we can directly connect the DC hubs using a DC cable, and we basically save a full converter station. Of course, this is a more complicated scheme, and we will completely change the system, and therefore also all the controllers that are governing the system. So from an expansion point of view, when we figure out how to design controllers that are expandable, this will be a necessary tool. But if we had to imagine that these HVDC links are from 3, 4, 5 different vendors, you can quickly realize how cooperation and these frameworks become complicated. Please, Ryan. This slide here is inspired by my wife. When we are in doubt what to buy, she just buys one of each. And this is also what we think we could possibly do on the island of Bornholm. The idea here is that we will make the connection both on the AC side and the DC side, as shown by the two yellow circles. If we construct the point-to-point and close the breakers on the AC side, then we can operate these as normal links, where we can have the DC breakers on the DC side as let's call it an innovative project expansion, where we can test the possibility to operate these links in a multi-terminal, multi-vendor environment. Should we fail due to either technical or regulatory issues, we can always go back and operate the links in the other way. If we didn't have the possibility to disconnect and connect on the AC side, then we could end up with a project that would be either significantly delayed or it may never be operable. So maybe this is something that could be a smart solution as an investment in the future. Brian, please. So next on technical challenges, I of course touched on some of them already, but we will mention a few more in the next slide. The first is not really let's say a technical challenge, but more a question, and it's a question you get to ask yourself when you start to design your power system from the beginning. We have voltage and frequency variations on the AC system onshore, and we design our components in accordance with this. But what if you in an 100% inverter-based system have very, very good frequency and voltage control? You could possibly reduce the converter size in the turbines, and you could possibly reduce the voltage and frequency range of auxiliary services or equipment. So maybe you could save per turbine a certain amount, and with all the wind that is being carried out, maybe you can have a much more cost-efficient system if you change the way we see normal operation. So this is at least an interesting question we should ask ourselves. The next interesting question would be how to regulate voltage and frequency. What sort of schemes do we see? At first, if you look at the AC bus bar, a traditional group approach would seem feasible, but simulation shows that due to the tight coupling between the components, there's a let's say a coupling with voltage magnitude and phase angle in such a way that you cannot simply decouple them and regulate them independent. So you will need let's say a hub controller to online monitor and handle these things. So the tight coupling between the components in such an extreme electrical system makes it necessary to devise new types of controls, and the classical ways of operating AC systems are being challenged. Of course, the dynamics of the system during events will be very interesting. There will be very tight coupling between plants, and adverse interactions are highly likely. So coordinated controls, shift of control modes, and then the whole philosophy of handling events needs to be thought of again in such an extreme system. Grid forming functionality will be an interesting topic. We had the idea maybe to optimize voltage and frequency to reduce cost of turbines, but what if we find that it's actually it's not feasible for the continental European system to have 300 gigawatts of wind if they are not participating in auxiliary markets, and if they are not providing some of the faster support functions the power system will need. Ryan, please. So maybe we should move the grid forming capability onshore and mitigate the reduction of rotating mass we see at continental Europe, and then move the grid forming capability to the wind turbines. This will of course not be something that reduces converter size and makes a more cost-efficient wind turbine, but maybe as an overall approach, this is better for the European system. So where to grid form and how to specify it is questions that we need to address in the coming future. Of course, on such a inverter-based system, the dynamics will be faster and they will propagate through the HVDC links to the onshore system where they will meet a system with other dynamics. So how will these systems interact with each other? Let's say that you have a 10 gigawatt hub and you have a largest contingency in Europe of 6 gigawatt. So basically, if you have adverse interaction between components out there and you have series of trips in after an event, if you didn't do your control tuning properly, then you are with the size of these systems putting the European system at risk. And of course, this is something that is completely unacceptable. And it could be shown that during normal operation, some of these bus bars will be separated to mitigate some of these risks, at least in the early phases while we learn to operate these systems. Ryan, please. A question that has been asked, where we have changed our mind a bit, is the question of whether we should add rotating mass. Should we add it for asynchronous condensers to increase system strength? Should we have inertia to keep the system in place, or is it actually better to be smart on your control tuning and then let the 100% power or Powertronic-based system handle it? There must be a significant difference compared to a 99% inverter-based system and 100% inverter-based system. And we have the choice of both up here. So what is the smart choice? The protection philosophy, you have a system with low short circuit level, there will probably be quite a number of high order harmonics in the signals. So how will traditional relays protecting cables and transformers, etc., react? We need to rethink that as well. Power quality management will also be a topic in itself out there, and hub monitoring and early warning, early prevention systems, and probably many more. Ryan, please. I will not say so much about the multi-terminal, multi-vendor solution. One of our major hurdles here is to assess risk and benefit. Is it a good idea to base future large-scale investments on unproven technology? At least now with the multi-terminal technology being immature and the multi-vendor technology being non-existent, should we somehow make some of the Danish islands the first pilot for this, or is it better to let somebody else go first? And how do you assess the risk and the benefit of such a choice? In any regards, somewhere down the line in Europe, we need to develop the technical and regulatory framework of interoperability for multi-vendor HVDC systems. And when this is being done, or has been done, then we can start discussing DC grid codes and DC control and operation schemes, and etc., etc. Please, Ryan. Sorry, this was a slide which was created in PowerPoint. So behind the picture, there's some points on expandability. I mentioned before that the significant difference compared to other projects is that we have to expand these over time, where typically the HVDC landed wind that has been constructed so far has been constructed as one project, let's say 2 gigawatts, and then that's a full stop. Here we want to expand the systems over time. So there will be a very weak offshore AC grid, which requires close attention on HVDC and wind power plant control systems. This is behind the figure. our colleagues in Europe, especially in Germany, have had a series of projects or problems on their projects, being the first to land wind using HVDC. This is a German article from the Spiegel, and if you know a little German, then this Knall auf hoher See is not a good it's not a good headline. The first 400 megawatt wind power plant was out of service for years, while the problems due to supersynchronous resonance issues that has not been captured in traditional design approaches was giving a lot of problems. However, as you see, the article is from 14, and many smart people have worked on these issues, and there's what is more or less turning into a standard. So such a system here can be designed today with little risk. Next slide, please, Ryan. So this is not what we have to do on the hubs. We will add HVDC and wind over time. And Ryan, please, again. So and we will do it again and again. So we are introducing additional equipment in an extreme environment, and of course you do not have to study power system engineering or power electronic control systems for long to identify a number of issues you need to address here. One question we have to address is how we should invest in such an uncertain future, the flexibility of control systems and equipment. How can we prepare ourselves for expansion? How can we prepare ourselves using the technology we have today to solve the future's solution? What is the smart thing to do here? Ryan, please. So wind turbines, we haven't discussed them so much, but here you have 3 HVDC vendors, and you could have 3 wind power plant developers, and you could have 3 wind turbine manufacturers. So interoperability between multi-vendors becomes complex at a new level. And one of the major hurdles is that when you are constructing, say, the first 2 links, then in the contracts you sign with the vendors, you have to somehow enable the possibility for them to share models with a future unknown, could be a competitor. And this is, from a contractual point of view, a very, very difficult exercise. Please, Ryan. So slightly touched upon it, but analytical tools and models for the design of energy hubs. So this is where I think we hit the target on the G-PST pillar 1 topic on analytical tool and models the most. The tools that we need for a future onshore power systems will be very similar to the ones we need on the hub. It will be quite clear that phaser-based models and study approaches will not be sufficient. So there will be a heavy burden of ENT studies that are carried out, and I think they will be supported by state-space eigenvalue and frequency domain methods in a way so that we construct a new toolbox for these hubs, and this toolbox can be taken directly to the onshore system. It will be the same with models. We, as system operators, are very fond of open source models built on, let's say, the classical mathematical functions, because they can be maintained and they can be used for the full lifetime of the assets. Where as soon as we go black box and we go compiler dependent, then there is a risk every time there's an upgrade of your EMT tool that your models will no longer work. So how do we ensure model maintenance capabilities if we have to rely on these specific black box models? The platforms that we are looking on, I will get back to them again, but we see a need to go for online studies as a part of the simulation package we have to carry out. And then an issue is that the models are specified through grid codes, and grid codes are not updated with ease. So it's quite time requirement to ask for new types of models and updates of existing codes. And we do not have much time here to facilitate such discussions. Please, Ryan. A hurdle that we are struggling a lot with is, if we go back to this diagram with the phases, that the model availability we have in these extreme systems, we need more complex models than we have. Basically, for us, for instance, in the specification phase to do design studies, this is quite difficult using generic models. You do not know how well you can trust them, but you do not have access to specific models until you get into the implementation phase and can work with vendors. So the whole model availability, and also here comes the same argument as before, where we do not have the experience from other projects that tells us what sort of models at what sort of detail level we should use and could use for these various phases. So this is something we need to learn as we move ahead, and also findings we can take with us when we go to transform the onshore system. Ryan, please. One benefit we have here when we start a power system from the beginning is that we can specify all the models we want, and we can have them for all plants out there. This is typically not what a luxury we have on the onshore system, where for older plants in Denmark, for instance, we have HVDCs as old as from the 60s. And at that time, we didn't ask for detailed EMT models. So when we're doing system level EMT studies, we quickly run into the issues of having available models. But one on the plus side on the hubs is that we can do this from the beginning. Another one on the plus side is that there are a limited number of plants out there compared to the onshore system. So it will enable us to do a long series of studies that are typically quite complex and sometimes even impossible to carry out on the onshore system. So I think, again, here there's a great learning experience in planning the system, designing the system, putting the system into operation, and then having used various models down the line, and then have the capability to measure response on the system and compare this to the models and validate their performance, and hopefully this can help us and vendors and OEMs to develop better models for future projects. Ryan, please. Another major issue we have is the ability to share models. Typically what we have done for smaller projects or projects that are in close vicinity of each other is to, through NDNAs, share detailed enough models. These little boxes are black box models. I try to illustrate that these are flying around between different parties that have a need for them. But in an energy hub environment, all plant owners, they will need to deliver detailed EMT models, but they will also need detailed EMT models of the other plants in the vicinity of their plant, and that means all of them to validate their performance. And such EMT models can typically not be shared between parties due to IPR, or at least it is very complicated and time-consuming to do. So we need some sort of new platform to enable the sharing of models. So something, as I have sketched below, where there will be some sort of closed network. It could either be cloud-based or a physical network, where vendors can work on their open models, but without access to the other models. And then through some parallel way of working, control tuning could be done for the whole system as a whole. One interesting question we need to ask ourselves here is that if you add, let's say, HVDC number 3, would you then expect HVDC 1 and 2 to be reconfigured? And should you ask plant owners to be available for such an exercise, and how do you formulate this in a contract when we do not know when and how these hubs are being expanded. But at least with the high penetrations we see onshore, this is an exercise we also need to take onshore eventually. So again, a great learning opportunity. Ryan, please. Sorry. One thing, this is a line from the Danish grid code that says that EMT models must represent all components, control system, and protection system relevant for EMT analysis. And particularly the last sentence has cheated us a few times. When we do studies on very, let's say, complex systems, typically a lot of cable, low short circuit power, and many inverter-based plants, then we see that what is typically needed in the models is different compared to a more classical system. And as vendors say, if we compile a model with all details, both short and long dynamics, then you will have a model you cannot cope with, because it will simply be too complex. And then vendors, they make assumptions on the behalf of the system operator, and system operator cannot specify needs and details, because we do not know what sort of protection systems are included in the plants. So this again, with new systems where we do not have experience, what is actually the right level of details for these models? Ryan, please. We see a need to expand capability on hardware and software in the loop. There will probably be a need to procure control replicas of all HVDC systems, control and protection systems, maybe for the wind turbines, maybe for the power to gas, and then somehow facilitate the cooperation between vendors, but also facilitate that studies are being carried out at a sufficient quality with as accurate representation as possible to ensure that we have a stable and reliable hub. But it's clear from a figure like this that this quickly becomes very complex and eventually unmanageable for energy hub type systems. You could imagine that if you expand such a hub over, let's say, 15 years, you would need to have a lab in operation for that time. You need to have trained personalities. You need to have somebody with knowledge on these systems, but they're not used that regularly when you're not expanding the hubs. So again, a level of complexity that we haven't seen on the onshore system that we need to handle through these hubs. Ryan, please. This was the last slide. I touched a bit on the analysis environment, and as Charlie said, next year we can go into some of the details. But for now, I want to thank you for your attention.
And Christian, we want to thank you for sharing that vision with us. It's really quite a visionary look at the future. A lot of challenges and a lot of opportunities, and it's going to be a pretty exciting time, I think. But first of all, before we go into the questions, I wanted to explore one or two areas with you. And one is about the genesis of this project. How did this vision come about? Where did the ideas come from, and how did they get to this stage of maturity?
It was
big idea.
Yeah. You see the need to harvest the 300 gigawatt, and you suddenly start to think creative. The idea originally came from Netherlands, where they started to look at this. In Netherlands, they are very skilled at constructing these sand banks that could potentially be artificial islands. So they had the islands and they had the need. In Denmark, we have very shallow water, so we do not need to go that far out seas to harvest wind. But it's not the same in Netherlands, for instance. So there a need drives innovation, and then you build on the thoughts, and then suddenly you have a vision like this.
It's quite impressive. And the other part of that question is, what kind of reception are you getting to this idea from both the general public and from the consulting and manufacturing community?
Um, there's a great interest from developers and from manufacturers. There's some skepticism in the public. This is new and this is big. The energy islands will be the largest investment in Denmark's history. And this is, of course, a high-risk maneuver. So will this be a successful? Will it give us a lot of problems? And all these questions are being asked. We haven't decided to construct the hubs yet, and there is a feasibility phase where we look at this very thoroughly. And if this shows to be an idea that is not ready for execution, then there will be a halt of the process. For now, at least.
Still some big decisions to be made.
Yes.
And the other area I wanted to ask about just a little bit was human resources, people. I think you're very fortunate in Denmark to have DTU and Aalborg University. And I'm just wondering, what do you see in the pipeline for people? Do you see the people coming out of the universities that you're going to need to carry this out? Are you looking other places for people? What's your assessment of the human resource requirements?
Yeah, the problem with constructing such an energy island is that you will need 10 years of experience doing very detailed stuff, and then you need to work with other people with the same amount of experience. And Denmark is a small country with very large ambitions, so we rely heavily on the ability to cooperate. I actually describe this as the mean of success of the energy islands. This will be our ability to cooperate. We cooperate a lot with the German TSOs that have similar ambitions, and we cooperate with G-PST that will help us on the tools and the methods. And then it's our task, more than develop everything from the beginning, to put the pieces of the puzzles together, instead of trying to drive everything ourselves. So international cooperation, and both at European and global level, will be a necessity for our success.
There'll be a lot of learning and sharing that'll go on as this proceeds.
Yes, and this is also why we are so keen to share approach and share what we do, because this is a motivating project for many, and many skilled people are already helping us out, and a lot of cooperation, both at university with research centers, etc., consultants is ongoing, and I only see this increases as we go into the details.
Yeah. Okay, let's turn to the Q&A there and pick some questions from there. The first one from Australia. See, hydrogen component is energy inefficient in production. Okay, so I guess producing hydrogen is not terribly efficient. So rather than direct DC to on-land pumped hydro storage, what's the thinking behind using hydrogen instead of trying to land DC and store it in something, well, pumped hydro, I guess?
Yeah, we are a bit outside my field of expertise here, but there will be so much wind, and we need hydrogen for transport. So we need the conversion to take place for storage of a fluctuating energy source we have in very large scale. So the question is not whether we need a hydrogen conversion. It's basically where and how to do it. It is inefficient now, but there's also very much effort put into it. A side strategy to the one on energy harvesting offshore is a power to gas strategy, also at European level. So I see a technology that is maturing, but again, I'm not an expert of this field.
Yeah, I would add also that if you look around the world at research that's going on for enabling very high penetration renewables future, hydrogen has really got a lot of attention right now. And if we make the same kinds of advances in hydrogen production, efficiency and cost as we have in solar and batteries in the last 10 or 20 years. I think that 10 years from now, the projections I've seen are that the cost of hydrogen will be competitive, for example, with the cost of natural gas today. So I would agree with you. That
Denmark is a 6.5 gigawatt peak system, and we have approximately 6 gigawatt hydrogen in pipeline for operation in 30. So these are actual plants of size between a couple of hundred megawatts to 1.2 gigawatt. They are there and they are coming.
Yeah, and I think Australia also has some very large hydrogen production goals in the next 10 years. So I think it's a global phenomenon now. Okay, next question has to do with the capacity factor of wind and offshore in Denmark is at best 50%. So you're going to be building a new transmission system, which is only going to be in use for half the time, 50% of the time. So I guess the question is about the economics of that.
Yeah, again, we're a bit outside my field of expertise. The idea is to again use the hybrid system so that the HVDC links can be used for selling capacity through the markets when they are not being utilized. They will be constructed so that they can take the peak production of the wind turbines, and then in low wind conditions you sell capacity to market. We have done this already on a system we call the Flytkjær, which is connecting Denmark and Germany. Here we have 1 gigawatt of German and Danish wind power, and then 400 megawatt connection to Germany. So in the case of low production, day ahead, this capacity is sold to the market.
Yeah. When you look at contingency requirements also, it's clear the lines aren't going to all operate fully loaded.
Yes, we have, until now in Denmark, traditionally we have used AC landing, and here the overload capacity is of course better, but here again the cables are being designed for the peak production of the wind power plants. And then the cyclic production with the cooling and the heating of the cables is taken into account in the design. But we do not have the same luxury with HVDC systems that cannot, like the cables, handle overloading.
Okay. A question on analytical tools. What are you using for planning and operation? I think you mentioned EMT for design, but I guess kind of a more general question for the planning of the system. What planning and operation tools are you considering?
Yeah, typically, most of the studies that are being carrying out now are EMT. Everything that will be done on the hub will be EMT. The problem is that you're using an advanced enough, let's say, domain, but the models we have, they are not vendor specific. So they are generic and let's say PLL and current controllers that are parameterized generic. So you can study typically outer loop behavior and device control strategies. But this is also just what we need now. We need to show whether the islands are feasible, and then in the next stage we need to specify some of the characteristics in more detail. So EMT studies on the hub and classical phasor domain studies onshore to study events where we lose parts or the whole energy island.
Yeah, I think the EMT tools are going to be pushed to their limits, and there's probably an opportunity and a need there for some advances both in the software design as well as in the computer infrastructure to run them on, I would guess.
Yeah, and the knowledge on what can you expect of generic models, in what sort of phenomena can be captured, which ones should you be careful about, which one do you need to know at which project stages for you to have a robust design at the end. Of course, we do not need to know all the details now, but we need to know enough to go into the next stage reliably. And this is something we need to explore, and we're doing all we can, and working also with consultants on these topics, simply over studying, also to learn.
Yeah, I think here's a comment from a skeptic, Christian. The bottom line is, why not use platforms like everyone else? But it's preceded by the observation that it sounds like you need to descope the performance, infrastructure, and wind services massively so the artificial island is cost efficient. Why not use platforms?
This has also been debated in Denmark, whether these Cajun structures or platforms should be used. Again, I think some of this was political decisions and the rest is put to the market. So for the electrical system design, from my point of view, I do not care if it's on an artificial island or if it's on a platform. So I will have to address this with a colleague.
Yeah. Okay, multi-terminal HVDC and circuit breakers been discussed for some years, maybe decades. How do you see the outlook for this? I guess it's the question of DC breakers always comes up. So what's your view of
at least
practicality?
The main vendors have them on stock, but I don't think anybody has them in operation yet. And so this is a bit the same comment as with the multi-terminal, multi-vendor. It would be nice to see this in operation in less complex systems onshore before we go massive and construct a system that relies on a technology which is unproven. So if circuit breakers, DC circuit breakers will be a part of the energy islands, and it will be if we go for a DC system, then we need to ensure technology readiness with the vendors before we go and use it on such large projects. And we are not there yet, but they have commercial breakers. They are ready to sell.
Okay. Okay, next one is still on DC circuit breakers or AC network CCT. Not sure what the CCT is. Either way, you'll need to respect maximum loss risk onshore with PNC, protection and control, solution offshore. 10 gigawatt loss of island is not acceptable. So I think you mentioned that the loss of a single biplane was your contingency design criteria, but what other thoughts have you had about loss of the island or more serious contingencies?
Yeah, the good thing about the island is that we are expanding them gradually. The first will be 2 gigawatt and the next will be 3. So we will build smaller systems and we may separate them even down to even smaller systems, and then we will get operational experience. And then through that, we will learn whether it's safe and reliable to connect to a larger extent, more gigawatts. At least from a market perspective, it's desirable that we have a copper plate on the hub or something that resembles a copper plate for us. If you have interconnectors between different countries, then you have free flow of energy between these. And if you start to separate the system to reduce risk, then you also reduce the benefit. But we would never go and construct a 10 gigawatt hub and then put it in operation in one go. This will be done over years.
Okay. CCT, critical clearing time. Okay, thanks. The next two questions I think we'll kind of take together. They, I guess, represent another point of view. You don't need to know how to tune an HVDC converter in an opened up model to understand the consequences of another and design another to operate next to it. And as well as you need to be able to host two different vendor models together and investigate solutions for them to operate together. The industry has done this for decades. So I think they're saying that there's some experience with parallel systems from different vendors operating together, but maybe you want to give the counterpoint to that, Christian.
Yeah, there are a few systems in service, but we do not have, for instance, at hub level, several HVDCs connected together in such extreme systems. So this is not comparable to, for instance, having two parallel HVDCs going shore to shore. That's been a Norwegian system where they have supplied two oil platforms using two HVDCs from two suppliers. And that was a significant effort to ensure that system. and this was only 2 vendors, and so the idea here is that I agree that it can be done, but we also need to make sure that it's efficient, and we need to develop a framework that allows us to do as much of the work beforehand, and then put what we can in standards and classical and well thought through ways of designing these systems. And then there will also always be project specific issues to address.
I think your example of the problem in Germany that took a couple of years to solve is probably an illustration of that point also, of what can really go wrong.
Yeah, and this is again the idea. In Germany, they had super synchronous oscillations between controllers, and I think it was capacitors somehow. And this is not captured in the classical way of approaching studies for such a system. And this, so simplifications are somehow inherent, and then you take them if you do system studies as you have done so in more simple systems.
Okay, so we're about at the top of the hour. We're going to need to wrap it up. Christian, thank you for a very informative and educational event. I know I learned some new things today, and I hope everyone else did as well. As I mentioned earlier, an email will go out once the video file has been posted, and we'll get the responses to your unanswered questions posted as quickly as possible. I see that there are a few left. We appreciate your engagement, and if you'd like to stay engaged, I'd like to invite you to the remaining sessions of the ESIG Fall Technical Workshop, being held virtually on Tuesdays and Thursdays throughout the month of October. Further information on the workshop and all of our webinars can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Christian, again, I want to thank you for this very timely webinar and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe. Thanks again for your participation. Bye now.